Previous sections, we've been discussing about the theories of conductivity, thermal conductivity, and diffusion coefficient of diffusivity. And these values are associated to the transport of energy or mass through the molecular mechanism. Okay, so that's going to be like collision for dilute gases, or actually collision of particles in suspensions, right? And now we're going to look at another form of energy transport, not by molecular mechanism, but by convection. So first, let's look at the convective energy transport, or convective transport of energy. Let's write that down. So that's the topic for today's discussion. So convective energy transport. Okay, so first let's draw a control area. Let's say we have a control area, and let's call it ds. So we have the control area having a normal direction in the x, normal in the x direction. Okay, so this is x and y and z. So ds is in the x direction, and it's forming a plane on the yz plane. Okay, so let's take a look at the rate of energy going across the control area. Okay, so the rate of energy being swept across ds, which is what? Which is the following, which is 1/2 density velocity square plus rho u times vx ds. Okay, so what are these? The first term here, you can see that it's the kinetic energy. Kinetic energy. And the second term here is the potential energy, or we call it internal energy. And the last part, Vx ds, this is what? This is actually dVx, which is the volume flow rate in the x direction. Okay, so if we look at term by term again, we see that the kinetic energy here, the kinetic energy, and this is actually per unit volume, which is 1/2 rho v squared equals to 1/2 rho Vx squared plus Vy squared plus Vc squared. And then we have the internal energy. Per unit volume equals to rho u cap. Okay. So if we look at this in 3 dimension, we can construct a 3-dimensional convective energy flux vector. So this is only in the x direction, right? Let's take a look at the 3-dimensional case. So the 3D convective energy flux vector it's going to be 1/2 rho v squared times rho u cap times the unit vector in the x direction times vx plus the unit vector in the y direction times vy plus the unit vector in the z direction times vz equals to 1/2 rho v squared plus rho u cap times v. Okay, so basically the convective energy transport here is basically just saying that if you have a volumetric flow rate of fluids flowing across some direction, the fluid itself will contain kinetic and internal energy, and that's going to be also going through that control area, and this is called what's been carrying with the fluid will be considered as a convective transport mechanism. Okay. So to go into a little bit more detail about the internal energy from a molecular point of view, let's take a look real quick. So the internal energy, U cap, and let's call this a molecular point of view. It equals to the sum of what? It equals the sum of kinetic energy of all constituent atoms and the relative to V and the intramolecular potential energies plus the intermolecular energies. Okay, we'll just kind of go through this. We're not going to go into the details. It's going to be the kinetic energy of all constituents times relative to V plus intramolecular potential energies plus intermolecular energies. And finally, to get the convective energy flux across a unit surface, you basically just need to figure out the dot product between the energy flux vector and the normal vector. Okay, So let's write that down. So to get the convective energy flux across a unit surface, with normal vector n, we have the flux equals to the dot product of n with the convective energy transport vector, flux vector. Okay, so by now we introduced the energy transport through molecular mechanism, which is the conduction, thermal conduction, and then we look at the convective energy transport. And there's also another way that energy can transport, which is by doing work. So let's take a look at that. Okay, so that's the work associated with molecular motions. So let's write it down. So this is the third mechanism for energy transport. So work associated with molecular motions. Okay, so basically let's take a quick review of the first law of thermodynamics. So first law of thermodynamics, basically that's the conservation of energy. So we have the change in internal energy equals to the heat exerted on the system plus the work exerted on the system, right? So Q here is the heat added to the system, and W here would be the work done on system. Okay, so let's assume we have, some control volume of fluid here experiencing some force F, causing it to move to another location. So let's call this moving dr, and this is our dw. So we know that the work here equals to dw equals to F dr, F dot dr. So the rate of doing work is going to be dw dt, which equals to F dot dr dt equals to F dot the velocity. Okay, so you can think of this as the fluid, exerting a force on the fluid from the minus side to the plus side. What does that mean? If we draw again our control surface, let's say we have control surface here. Again, we have x, y, and z. So x, y, and z. And this is our ds. And then we have some shear stress or normal stress, pi x. This is our normal stress. Okay, so basically what that means is that the fluid on the negative x side exerts a force which is pi x ds on the fluid in the plus side. Okay, so finally, if we go into the fluid mechanics part here, we know that the force here is basically F. So the rate of work done by the fluid at the negative side to the plus side is pi x dot ds, or it doesn't have to be dot actually. I guess I should say pi x dot v times ds. So, if you look at these work on the three directions, so for x, y, and z direction, we know that pi x dot, so the flux vector in the x direction is pi x dot v, which equals to pi x x vx, so this is our stress tensor, plus pi x y vy plus pi x z vz, which is also defined as pi dot v in the x direction. So you can also write down the y direction, which equals to pi yx vx plus pi yy vy plus pi yz vz, defined as pi dot v in the y direction. And finally we have pi z dot v equals to pi zx vx plus pi zy vy plus pi zz vz, and defined as pi dot v sub z. So finally we can define or come to the definition of the work flux. So work flux equals to the unit vector in the x direction times pi x dot v plus delta y times pi y dot v plus delta z times pi z dot v. Again, if you need to know the rate of work across a unit area with some normal vector, you basically just need to figure out the dot product between that normal vector and the combined work flux. Okay, so again, let's write that down. So rate of work across unit area with normal vector n is going to be n dot pi dot v. Okay, so again, let's quickly kind of review this part again. So the work associated with molecular motions. So basically, from the first law of thermodynamics, we know that the internal energy equals the heat, or Q plus W, right? And Q is the heat added to the system, and W is the work done on the system. So the work done on a system is basically, if you draw a control volume, and that control volume is, moved with some dr by the force F, then the work associated with that would be dW equals to F dot dr. And if you look at the rate of that, you just need to take the derivative of the work with time. And that tells you that the rate of doing work equals to the force dot the velocity. And from fluid mechanics, we know that the force here is basically the stress exerted. So maybe we shouldn't call this normal stress. I should just call this stress in the x direction. So the stress in the x direction times ds would be the force, right? Times the unit area. And so from fluid mechanics, so we can, that the stress tensor here is always, because it's a tensor, it has two components. So basically down here, for the x, y, z direction, I'll write down all components for you and show you what the work flux combined looks together. Okay, so remember that up to now, we have basically introduced all mechanisms of energy fluxes. So we start with the thermal conduction, then we introduce the convective energy flux, and finally the work flux. So it's a good time for us now to introduce to you what's called the combined energy flux vector, and this is basically the most useful tool, or it has a very comprehensive information for you to use during the next chapter when you're going to use shell balance methods to deal with different problems. Okay, so let's get to this introduction of the combined energy flux vector. So I'll put a star here because this is very important. So combined energy flux vector and we use the symbol E. So E is defined as everything add together. So we have the convective energy flux, work flux, and the molecular mechanism, right? So we just introduced the convective flux equals to 1, so the kinetic energy plus internal energy times the velocity. And then the work flux would be the stress tensor, the dot product between the stress tensor and the velocity. And then finally we have Q, which is heat conduction by molecular mechanism. So if we draw this one by one, this is our convective energy flux. This is work flux. And this is, let's just say conduction. Let's call it a molecular mechanism. Okay. And before we continue, we can take a look at the molecular stress tensor here. So if you look at the molecular stress tensor, which is actually introduced in fluid mechanics, so the molecular stress tensor, so it's going to be pi, and it's basically equals to the pressure term times the shear stress term. Okay, so basically the work associated here, the work flux, can be divided to a pressure term and the shear stress term. Okay, so basically the first term here would be pressure force, and the second term is the viscous force, because it's shear stress. Okay, so with this defined, we get to the following, right? We get to rho u v plus, so let's try not to jump steps. If you go back to our combined energy flux vector, we have decoupled the work flux to two terms, the pressure force and the viscous force. If we combine the pressure force here with the internal energy force or internal energy term here, so if we combine these together, what we get is rho u dot v plus p dot v. Sorry, can't write. P dot v. Based on thermodynamics, this u plus pv is the definition of enthalpy. So we can kind of rewrite this as rho u plus p over rho times velocity equals to rho times u plus pv cap times v, and this equals to rho delta h cap or h cap v. So we can rewrite the energy flux vector using combining the pressure force and energy to become the enthalpy term. So we can write again as the energy flux vector equals to still the kinetic energy term, 1/2 rho v squared plus rho h cap v, h cap times v plus the viscous shear stress term plus conduction. Okay, and this is a quite important conclusion here. Let's rewrite the E so it doesn't look like a row. Okay, so if you have a surface for a surface element ds with normal vector n, the dot product between n and the combined energy flux vector is the combined energy flux. From the negative to positive side. Okay. And before we continue, I would like to give you some notes about the shear stress tensor, momentum flux tensor, this thing here. So I'll just say note, and you can find this in chapter 1-2. So the tau here is the viscous momentum flux tensor. And tau equals to negative mu gradient V plus gradient V star, or plus 2/3 mu minus kappa times delta gradient V . Okay, so for example, if you have a stress tensor in the IJ, it is equal to negative mu times partial V, partial Vj, partial xi, plus partial Vi, partial xj, plus 2/3 mu minus kappa times partial V x partial x plus partial Vy partial y plus partial Vz partial z ij. Most of the time, actually, we don't need to deal with the later part in most cases. So usually we just need to focus on the first part. Okay, so that would end our introduction to the theory of thermal conductivity, and also the introduction to the combined energy flux vector. Remember the key essence here. Let's go back a little bit to the combined energy flux vector. The essence is that we have three mechanisms for energy flux transfer. One is the convective energy transport, one is the work associated, and then it's the conduction, or based on molecular mechanism. And what we're doing here is basically just rewriting this equation such that we combined part of the convective energy flux with part of the work flux. So we combine the internal energy and the pressure force term here to become the enthalpy term. So after this derivation, we have the convective transport combining using the enthalpy instead of the pressure term separated, and the work associated only focusing on the shear work, or the work through the work done by shear stress, or the shear stress tensor, plus the work by conduction, or the heat flux through conduction. Okay, and in the next chapter, we will introduce how we use the combined energy flux vector to perform shell balances of heat transfer problems.